Yeah, so I'm going to talk about a class of problems that are slightly different from the things you have seen so far in the workshop, I think. And I'm going to give you two approaches for the problem. One happens to be more general than the other, but somewhat paradoxically, I'm going to be talking more about the less general one because it leads to more interesting information about the models. Okay, so what are these problems? So these are actually very natural problems. These are just average computation problems. So which averages? So let's look at independent sets. We know that computing the maximum size of an independent set is NP hard. Computing the number of independent sets is number P hard. Those are classical results. And the kind of question you want to ask is, what's the complexity of computing the average size of an independent set? You can ask the same question for matchings. Again, the max matching and number matching problems are well known in complexity. But again, we want to know what's the complexity of computing the average size of a matching. Now, this might look a bit sort of ad hoc, but this kind of question arises very naturally in the statistical physics setting. So let's now look at the Ising model. Again, the partition function is a very well-known number P hard problem. And what we want to look at now, what these averages correspond to, are very important statistical physics quantities like mean magnetization. So this is just you have the Ising model. I'm parameterizing it as a sort of edge, as a cut generating polynomial. So for each cut, I have a weight for it, which is lambda to the number of plus spins and beta to the number of the sort of the unsatisfied edges. And now we might want to compute the mean magnetization, which in this case would just be the average number of plus spins in the system, where the average is taken with respect to this distribution. Similarly, you can ask for the mean energy, which would be the average cut size, so the number of unsatisfied interactions, with respect to that Gibbs distribution. And we want to understand what's the complexity of computing these questions, and maybe also try to understand if that depends upon whether the mod is ferromagnetic or antiferromagnetic. So the question is why do we want to study averages? And we don't need to ask that question because we already know that we have studied averages a lot in the approximation setting. In fact, sampling, the problem of sampling from the Gibbs distribution sort of draws its importance from the idea that it can be used then to compute these samples, because these averages are actually the interesting physical observables that you want to know about a model. And the sampling problem becomes important because then if you have samples from distributions close to the Gibbs distribution, you can actually approximate these averages. But it's somehow, surprisingly maybe, the exact computation problem for averages has been somewhat ignored. So in some cases it's trivial. So for the Ising model, for example, if you have no field, which corresponds to lambda equals 1 in its notation, then the magnetization is just half, and it's the number of or n over 2. But what you want to know is what happens at other lambda, and what happens to other averages like mean energy, and what happens to these other models like independent sets or matchings. And so those are sort of the application-based regions. But one thing that we'll see in this talk is that asking this question about the exact computation of average also leads to new questions about the complex zeros of partition functions that sort of arise very naturally out of studying the complexity of averages. Okay, so that's the goal. So what are the results here? So let me just not hold any suspense here. So we can show that all these averages are number P hard. So average size of independent sets, average size of matchings, the Ising mean magnetization for both ferro and antiferro, except for that one point when the field strength is 0, and as well as the Ising mean energy. However, for most of the talk, these are new results like in last year, but for most of the talk, I'll be talking about some earlier results which only looked at the ferromagnetic magnetization and some cases of matchings. And in doing so, we'll see a connection to Lee-Yang type theorems, so theorems about complex zeros of partition functions, and in fact some new versions of these Lee-Yang type theorems, and we'll see how these come into play into the average computation. So any questions about the models or? Okay, so let me start with a recap of how n number P hard is proven. I mean, shouldn't probably have the slide in this meeting, but still let's go over it. So typically, if you have a partition function, you know that it's a generating polynomial of some sort of interesting combinatorial structure. So for the Ising model, for example, it's enumerating cuts among other things, and so you can sort of try to use this polynomial to show. I mean, the fact that this polynomial encodes these hard commutative structures can be used to prove its hardness using the interpolation idea. So more formally, you view the partition function as a polynomial in one of the parameters, in this case the field strength, and now the coefficients of the polynomial encode the solution to some number p hat problems. In this case, it would be number of max curves, for example, for the Ising model. And now somehow, if you know how to compute the partition function, then it's a small degree polynomial. The degree is just the number of vertices. So you use evaluations of the partition function to compute these coefficients, and because these coefficients encode a number p hat problem, you prove that the original partition function itself was number p hat, at least when this parameter is a part of the input. And then you can do some work to remove that restriction and show that somehow you can simulate different lambdas and prove hardness even when the lambda is fixed. So you somehow change your graph a little bit to simulate different lambda, and then again use this strategy to show that you can, if you could have compute this polynomial, then you could compute these coefficients which encode these number problems. So that's the usual strategy for proving that partition functions are hard. What we want to do now is something different, which is averages, where something like this might work, but will have to be modified a bit. So let's try to do that. So the magnetization also encodes all these coefficients. So let me look at the Ising magnetization, for example. So here now the magnetization is just the average number of plus spins with respect to those Gibbs distribution weights, and I mean it's a consequence of the definition that it's a ratio of the derivative of the partition function with the partition function. So all the coefficients of the partition function are still there, so you can still try to somehow, using evaluations of the magnetization, you can still try to extract them. So what would that mean? Well, now you, instead of viewing this as a polynomial, you view it as a rational function. The coefficients still encode the solution to the same number p hat problem because the partition function is still sitting there. And now you somehow try to use some kind of rational interpolation to figure out these coefficients. The problem is that rational interpolation does not typically work. I mean, if you have a rational function p over q, and here's a somewhat funny example. So those two rational functions are equal, and any algorithm that you have which just gives you black box access to this rational function cannot distinguish between these two representations. So there's no way you can figure out the coefficients of one. So basically, if you have common factors, then in general you cannot interpolate. You cannot find out. You don't have access to the coefficients of the rational function out of interpolation. You have access to the coefficients of some reduced form, but that reduced form does not necessarily encode the solutions to these number p hat problems. Okay, so that is a roadblock you run into, and that immediately suggests that a remedy, which is, well, so somehow ensure that p and q don't have common factors, and then you can of course do things. So that's the first approach, that you can try to show that p and q don't have common factors. So that's the first thing we're going to look at. Second thing you might try to do is that use the special form of these rational functions. So these are not any arbitrary rational functions. They basically come from derivative of the log. So they can be seen as derivatives of the log of the partition function. So maybe you can use that structure to somehow do something which I very cryptically note here as integrate the mean. So we'll look at this in the second part of the talk. For this part, let me concentrate on the first thing, which is to try to show that, at least in some interesting cases, these two polynomials will not have common factors. The partition function and its derivative will not have common factors. Okay. So that's what we do. Okay. So, and in that case, so that's at least a necessary condition, but it's also sufficient. It's not hard to show. It's sort of folklore result that if you do have a rational function where you know that the numerator and the denominator don't have common factors, then you can efficiently determine all the coefficients using basically the same technique as solving linear equations as Lagrange interpolation. So in our case, our rational function looked like lambda times the partition function, the derivative of the partition function divided by the partition function. So all we want to do is to show that the GCD as polynomials in lambda of the partition function and its derivative is 1. And this is where complex zeros enter, because that condition is equivalent to saying that the partition function and its derivative don't have any common complex zeros. So we are only interested in the physical setting where all the parameters are positive real numbers, right? Lambda and beta are all positive. But we are sort of naturally led to this question of asking questions about the zeros, the complex zeros of the partition function and its derivative. Any questions?
That's just double roots.
Yeah, so like there are many equivalent ways of saying this. So you want to say that the partition function does not have any double roots. Now, and just to sort of recap all of this, so if you believe me so far, then what we know so far is that if we can show that partition function and the partition function and its derivative have no common zeros, in other words, the partition function has no double roots, which is the same thing, then the magnetization is as hard to compute as the partition function, because you can do rational interpolation, figure out the coefficient of the partition function, which is number p hard, and so on. Okay, so now, I mean, of course, this is not always true, because disconnected graphs can have common zeros. If you have two copies of the same graph, then the partition function is just a square of the partition function of the original graph, right? And then, of course, it has all its roots are double roots, so it shares all its roots with its derivatives. So that's fine. I mean, that's a sort of a boundary case, but it does suggest that we sort of need to study the zeros of the partition function, and this has been done in statistical mechanics for a very different reason, which is that of studying phase transitions. And one very striking sort of specimen of such a result is the Lee-Yang theorem. So this is only for the ferromagnetic Ising model. So you look at the ferromagnetic Ising model. So that means beta, the edge interaction strength, is between 0 and 1. And you look at its complex zeros, where thinking of it as a polynomial in lambda. And what the theorem says is that all these zeros lie on the unit circle in the complex plane. So all these zeros have magnitude 1. It does not say anything about the zeros of the derivative, but you can get some information. So, I mean, from sort of very basic complex analysis, that the zeros of the derivative lie inside the unit circle or on it. So, if they are double zeros, they lie on the unit circle, but all the other zeros lie strictly inside the unit circle. But of course, this does not get around our previous counterexample of disconnected graphs, because in the case of disconnected graphs, all the zeros will lie on the unit circle for both z and z prime. And they'll just be the same zeros. But still, I mean, this is pretty exciting. I mean, offhand, you don't expect why something like this should be true. But there is one good reason to sort of intuitively believe why this should be true, even before you have a proof. And we'll see a proof of this. And the reason is this, which is that the sort of the main symmetry of the Ising model is a plus-minus symmetry. If you change pluses to minuses, the model doesn't change. And that symmetry means that you change lambda to 1 over lambda. So in some sense, the only place where the zeros could lie would be sort of a curve which is symmetric under this transformation, and the circle is sort of the only curve. So that's not a proof, and I made a lot of wrong statements there, but it shows you why that should be true. And basically, the proof does use this fact that it uses symmetry crucially, and we'll see that later. And it's the only fact that it uses. But still, I mean, so it's all very good. It says something very striking, but it does not help us because, as I said, the only thing it says about the derivatives is that those zeros lie either on the circle and then they coincide with the zeros of the partition function, which is bad for us, or they lie inside. Okay. So the next step is to somehow get around this, and that's what we did. So the main theorem that we proved is that if the graph is connected, so we just dump our counterexample. If the graph is connected and if beta is strictly less than 1, which is again saying that the graph is connected, because if beta is 1, that means the graph is completely disconnected, then the derivative, all the zeros of derivative lie strictly inside the unit circle. So they don't. So the Lee-Yang theorem would say that the zeros of the partition function lie on the unit circle. Gauss-Lucas would say that they lie. So the zeros of the derivative lie inside the convex hull, so they lie on or inside the unit circle. And this theorem is saying that if the graph is connected, then they actually cannot coincide with the zeros of the partition function. They all lie strictly inside. So that says that the zeros of z and z prime lie in disjoint sets, so they cannot be equal, and hence z and z prime have no common factors, and you get that result. Okay. So for the rest of the talk, I'll first. So let me give you a preview. I'll first give you a proof of the Lee-Yang theorem, and then show how you can extend this to this setting to show that the partition function does not have double roots. But then we'll see that this kind of an approach cannot be pushed too far. So for some other models, you don't have results about zeros which are as strong as the Liang theorem. And then we'll see another approach to sort of prove these hardness result at least for these monolithic independent sets and so on. But that can come later. For now, let's concentrate on just looking at these series of polynomial results. Okay. So any question about the setup of the Liang theorems or? So how do you prove a theorem like the Liang theorem? Somehow the answer is that you make the problem harder, which is that you look at instead of looking at the usually using partition function, you look at the multivariate partition function, which is basically the same thing. Now the weight of each configuration is, again, you have each frustrated edge gets a beta factor, but each vertex now has its own field. So there's a different lambda for each vertex, and all the plus ones, all the plus vertices get their own ZV. Okay. So given that weight, you can again define the partition function, which is just the sum over all the configurations of these weights. So it's nothing much has changed. But now you want to, but we'll also need to be looking at these more general. We'll also need to be looking at generalization of our theorem, which is about the derivative of the partition function. So you need to generalize the derivative a little bit, and it turns out that the right sort of derivative to look at is not just the partial derivative, but something slightly scaled. So we look at the derivative that we are going to be looking at is so you go over all the variables and you look at the partial derivative, but you multiply it by the variable itself. So it's like taking the partial derivative with respect to the log of the variable rather than the variable. So and then the magnetization is just this derivative really. So divided by the partition function. So the magnetization with these fields is just the derivative of the partition function computed according to this d operator divided by the partition function, and that agrees with the univariate case when all the fields are equal. So that's just some notation. So given that, what does the Liang theorem say in the more general setting? So now you have different fields for all these vertices. So remember the earlier things said something which is very easy to state, that if the partition function is 0, then then the single field has to lie on the unit circle. Now there are multiple fields, so you cannot make a statement like that. But what you can say is that if it is the case that all the fields are on one side of the unit circle, so all of them are bigger than 1 in absolute value, or all of them are less than 1 in absolute value by symmetry, then the partition function is non-zero. So that's what Li and Yang proved. So it's the same setup, but if all the fields are on one side of the unit circle, they might be unequal, then the partition function is not zero. And if you set Zi equals Z, then you get that this is not 0 if the field is bigger than 1, and then by symmetry you also get that it's not 0 if the field is less than 1, and so you get the Liang theorem. And similarly, what our theorem says in this setup is that if you're on a connected graph now, and you have this condition that beta is strictly less than 1 again, which is saying that the graph is connected, and all the fields are less than or equal to 1 in absolute value, then the derivative does not vanish. And now you cannot use the symmetry. The derivative does not have that nice symmetry. But again, if you set all the zi's equal to z, then you recover the old result, which is that the derivative of the univariate partition function is not 0 unless the field is inside the unit circle. So those are the multivariate versions. So these kind of results have a name in the literature, and they're called stability results. This particular kind is called stability with respect to the unit circle, but you can sort of define stability with respect to other so-called circular regions like the half planes. But go there. Okay. So now we want to see how we'll prove one of these things, and I'll start with the Liang theorem. It has a pretty nice proof, and the proof we'll look at is due to Asano. It's a very simple induction, and somehow the only calculation happens for an edge, and that calculation only uses a symmetry. So let's look at that proof, and then we'll come back to the proof sketch for our theorem. Okay. So we want to prove the Liang theorem in the multivariate setting. And let's say so I mean, we'll try to prove it by induction. So let's say that a graph has some property A. So A is for Asano, who came up with this particular kind of proof. If the Liang theorem holds for that graph, which basically means that if beta is between 0 and 1 and all the fields are bigger than 1 in absolute value, then the partition function does not vanish. Okay. And so one thing to note, I mean, something very abstract, is that if there are two graphs, Z and G and H, and they both have this property, and you just take their disjoint union, then the partition function is just the product of the two partition function, and that also has this property. So this sort of survives products, unlike the derivatives, but that's fine. So as I said, there's only one calculation in the whole proof, and let's do that calculation. So let's show that the Liang theorem holds for one edge. Okay, so for one edge, there are two fields, Z1 and Z2. This should be a beta. And now the partition function is just this. It's Z1, Z2, which is when both are plus. There's a 1 when both are minus, and there's beta Z1 plus Z2 when they're plus, minus, or minus, plus. So that's the partition function. And we want to show that that has this Asano property, which means that if it's 0, then at least one of them has to be less than or equal to 1 in absolute value. Okay. So we want to show that, or in other words, that this cannot be 0 unless if both of them are bigger than 1. Okay. So let's do that. So suppose that this polynomial is 0. Suppose it's equal to 0. Then just by rearranging, we get that say one of them, say Z2, is this function of Z1. So and I just take absolute value. Now, so this is where the symmetry comes in. This is a transformation of the complex plane which fixes the unit circle and takes the outside to inside and the inside to outside. But this happens only when beta is less than 1. So that's where the ferromagnetism comes in. So all the sort of constraints of the Liang theorem just come in at this juncture, and then they don't come in again. So this transform. So this transformation of the complex plane, which is 1 plus beta z over beta plus z, it fixes the unit circle, and that's not hard to see. It also takes the outside of the unit circle to the inside, and the inside of the unit circle to the outside. But this happens only when beta is less than 1. If beta was bigger than 1, then again it fixes the unit circle, but then it keeps the inside the circle and the outside the circle. So this sort of flip occurs. Now, but we are in this case, so we are in good shape. And why are we in good shape? Because, well, what would happen if suppose suppose Z1 was bigger than 1, then this thing means that for this polynomial to be 0, Z2 is this transform of Z1. So if Z1 was here, then Z2 has to lie inside the unit circle. So they both cannot lie outside the unit circle if the polynomial is 0. So that's the only calculation, as I said. The rest of Asano's proof is completely generic, and that's the only place also where the ferromagnetism comes in. And the rest of Asano's proof is quite sort of general, and here is what it is. So there's sort of one inductive step, which is to sort of merge vertices. So what the proof would look like, and we'll see an example, is that if you want to prove the theorem for a general graph, you take all the edges of the graph, and sort of think of them as disjoint edges. For each of those edges, you have the theorem, and then you throw all the edges together. So each vertex has multiple copies now. And for this new weird graph, you have the theorem because of this property. And now you start merging different copies of the same vertex. And you want to show that the theorem survives this merging step. So what does the merging step look like? Well, if you have sort of two copies of a vertex, the partition function in this graph where there are these two copies looks like, so A, B, C, and D are polynomials in the activities of the other vertices. And the partition function looks like A times Z1, Z2 plus B times Z1 plus C times Z2 plus D. So basically you just look at all possible 4 configurations of these two vertices and just expand the partition function in terms of those 4 different states. And now what would it mean to sort of merge these two vertices? Well, it will mean that you get rid of these 2 configurations. So now you only look at those configurations in which those 2 vertices had the same state. Either they were both plus, which corresponds to this, or they were both minus, which corresponds to this. So if the partition function for the original graph looked like A Z1 Z2 plus B Z1 plus C Z2 plus D, then the partition function for the new graph would be a polynomial in all the other variables and a new variable z, and it would look like az plus d, where a and d are the same as before, and they are polynomials in the other variables. So that's just a property of partition functions. There is nothing about the Ising model here. Okay. Well, the only thing about the Ising model is that there are two spins. Now what we want to do is to show that if this graph had the Asano property, then this new polynomial also has the Asano property. Okay. So let's start with this. So this had the Asano property. So that means that if so let's fix all the other guys so that they are bigger than 1. What the Asano property now implies is that if z1 and z2 also are bigger than 1 in absolute values, they're also outside the unit disk, then this polynomial will not be 0. Okay. So that's just using the Asano property. But now let me do something more, which is let's fix z1 and z2 to be equal. Then I get that this quadratic polynomial, which is az square plus bz plus cz plus d, which is just obtained by setting z1 equal to z2 equal to z, is also not equal to 0 if z is bigger than 1. Because all of these other guys are bigger than 1. But that means that the product of its zeros is also, so if it is not 0 when it's bigger than 1, then it has zeros, of course, because we are in the complex field. So all the zeros have to lie on or inside the unit circle. So their product in particular also has to lie on or inside the unit circle. And hence you get that the product, this is just using some high school algebra, that the product of zeros of a quadratic equation is just d over a. So d over a has to lie inside the unit circle, which is just in a d over a has absolute value less than 1. But that's precisely the condition that this guy has a Asano property, which is that. So what does it mean for this polynomial to have the Asano property? It means that if z3 to zn are all bigger than 1 and z is bigger than 1, then this is non-zero. But this is precisely saying that, because for this to be 0, z would have to be d over a. So if all of these are bigger than 1, then the absolute value of z would have to be less than or equal to 1. So again, so notice that this did not use anything about the Ising model or about the system. So all the symmetries and all the properties of the Ising model were just used in the case of a single edge.
So is it because A is equal to 0?
Yeah, good point. Yeah, it is not, but you need to, so I pushed that under the rug. So you can sort of use the theorem inductively to show that it's not, that A cannot be 0. Okay, so let me now show you just an example of how the theorem works. So suppose that we want to prove, so we have these two things that we proved, and now we want to prove the theorem for a general graph. So it's just a illustration of what I said earlier. Suppose you want to prove that this graph has the Liang, so the Liang theorem holds for this graph. You first start off with all these edges separately. You know that all the edges have the Liang property because of the first thing we showed. And in fact, this whole graph, which is a disjoint union of these edges, also has this property. And now you start merging vertices. So you first merge those two. That has a Asano property. Then you merge those two. Then you merge these two. Then you merge that merged vertex with the third one. And now you have this graph that has Asano property. And you can do this with any graph. And that's how the Liang theorem is proved. Okay, so that's for the Liang theorem. Now we want to do the same thing for our theorem. And again, we define this property, which is basically what the theorem says, that the derivative is not 0 if all the fields are bigger than or equal to 1. So the crucial thing is that there's a equality also here. So now again, we start off with, so in this case, it won't be the case that all the model specific details are in the base case, but let's do the base case anyway. So the base case is again a single edge, which is the partition function is again as before, z1, z2 plus beta, z1 plus z2 plus 1. And we want to prove that this theorem holds for that. In fact, it turns out to be even simpler than the Asano case. So the fact that the derivative is, so the derivative happens to be 2 times z1, z2 plus beta, z1 plus z2. And if it is 0, that means that 1 over z1 plus 1 over z2 has to be bigger than 2 over beta. But if both of these guys are bigger than 1 in absolute value, and beta is strictly less than 1 in absolute value, this cannot be true. So you have the theorem basically for free for a single edge. Now the main issue, the first issue that you see is that you cannot now throw all the edges together because the theorem fails immediately. For multiple copies of the same graph, we know that the theorem is just false. So we cannot use that step. So we have to be more careful, and we still have that contraction step of Asano, but we need to be more careful in adding new vertices, and we have to keep adding these new vertices while always maintaining connectedness to the graph. So I won't go into the details, but it's basically for each step you show that the property is maintained, and these steps sort of depend upon some correlation inequalities for the Ising model, for the ferromagnetic Ising model. But then the structure of the proof is similar. So you basically construct the graph one step at a time by basically adding a new vertex, and then sort of merging copies of the same vertex. Okay.
Is that the Donald-Newman lemma?
Excuse me?
Is 74, is that the Donald-Newman lemma?
No, Donald Newman. No, I don't. I think it's just Newman.
No, which Newman?
Oh, which Newman? Charles Newman. Okay, but yeah, so that's one proof. There's also another proof that we came up with later, which is slightly shorter and more analytic rather than this combinatorial construction of the graph, but it proves a slightly weaker version, but which is still sufficient for the application. Okay, so basically, once you have this theorem, then as I said earlier, you get the result for free. So you get this fact that the partition function zeros lie in a set that is different from the set in which the derivative zeros lie, and so you can do rational interpolation because there are no common factors, and you can compute migration. And then you can also get it for bounded degree graphs by using the hardness result for the partition. So basically, you can translate all the results for partition functions to this setting at one sort of technical cost, which is a degree increased by 1, but that's not very important. Okay, so far everything. So just to recap, so far everything is for the Ising model, and just to recap, it's like we basically showed the Liang theorem said that the zeros of the partition function lie on the unit circle. Our zeros lie strictly inside the unit circle, and you can use and we show that means that the mean magnetization of the ferromagnetic Ising model is number p hard, and then we sort of run into trouble. So far so good. So we get this nice information about the zeros of the Ising model partition function, which we did not have before. That zeros are non-degenerate and so on. But now the strategy starts failing for other models. For example, for the antiferromagnetic Ising model and independent sets, you can actually find examples of graphs where zeros, like of connected graphs where zeros are repeated. Also, there's no analog of the Liang theorem for the antiferromagnetic Ising model. So basically for this region, so again, everything fails at the edge. So the zeros fly off the circle in some sense. And if you're now looking at the mean energy, which is just even for the ferromagnetic Ising model, which would correspond to a derivative with respect to beta, then again you can have the same kind of behavior. You can have common zeros between the derivative of the part and the partition function, and again you have no analog of the Liang theorem. So basically, this kind of information about the zeros of Z, so far at least, is available for very limited classes of partition functions. Ising model is one, the monomer dimer model is another, where there are very strong results known. And there's very weak results known for independent set model. And in fact, I mean, the exact analogs are false, so it's not surprising that they are not known. Okay. So that leads us to the next part of the talk, which would be just proving all the other results after circumventing Liang type theorem. So it's a completely different approach to proving these hardness results. So before that, any questions about Liang? The Liang theorem? So now, as I said, the second approach was to somehow integrate the mean. That was a 3-word summary I had, and here is what that meant. Well, I mean, the magnetization is, as I said, it's basically the derivative of the log of the partition function. It's the first derivative of the free energy. Now that means, in particular, that the log of the partition function is the integral of the magnetization. I mean, that's not very earth-shattering, but that's true too. So one sort of strategy for proving that the magnetization is hard is to say that, well, if you could compute the magnetization at enough number of points, then we could just perform this integration, compute log Z, and that we hope is hard, and then we are finished with the reductions. but the problem is we are looking at exact computation, and we sort of, if we are looking at a fixed lambda, then the only thing we can do is compute this guy at some n different values of lambda, but we don't have much control over which n values of lambda. So if you're going to sort of do this kind of thing of simulating different lambda by modifying the graph for a fixed lambda, then the different lambdas that you simulate are not sort of under your control. And then even after that, you will need to have very good bounds on the quadrature. So with these points on which you have no control, you want to show that somehow the error in this sort of numerical integration is not too bad, and you have some good estimate of the log partition function. So that doesn't seem to work. But something very related will work, and that is, instead of doing numerical integration, you do symbolic integration. So you try to compute some form of the partition of the magnetization, and then symbolically integrate it to get the log partition function. So far I've said sort of nothing, but let's see how this could be done. Okay. So let's say that. So the basic issue here is that of course if z and z prime had no common factors, and by what we said before, we could just compute the partition function just by interpolating. So the problem comes only when there are common factors. So let's say that there are common factors between z and z prime, and the GCD is some g, some polynomial g, which we don't know. That means that the partition function, that the magnetization looks like a over b lambda, where a and b are basically the rest of the factors of z and z prime. Right? So a is z prime over g, and b is z over g. Okay. So now, in fact, like if there was some sort of if you look at the sort of the unique factorization of z as a polynomial over the rationals, then this g and this polynomial g, b, and a can all be written down in terms of those polynomials very nicely. So, for example, because we are just looking at the GCD of z and z prime, g is just, so if z had the factorization product of pi, each polynomial pi raised to di. So these pi's are not something we know to begin with. Then the GCD would just be pi raised to the same powers, so this should be di. So di minus 1. Right? And this polynomial b would just be the product of the pi's. So basically, what does symbolic integration mean? It just means that we find the pi's and di's, because then we know log z. So how do we do that? And this turns out to be quite easy. So in some sense. So the first thing is to sort of just observe that, you can, with rational interpolation, you cannot find z and z prime, but you can find a and b. So so because you know their degrees and so on, you can compute a and b with just any poly n values of lambda. So this is something you can do. So now that you have a and b, here is sort of the full sketch of the reduction. So you compute a and b first from the interpolation. So you interpolate mu at n values to get a and b. Okay. Now the pi's are determined uniquely by factoring b over the rationals. Okay. So the pi's are the irreducible factors of b over the rationals. So they're determined uniquely by b. Now once the pi's are determined, the di's are determined by a partial fraction expansion of a and b. So that's also a polynomial time operation. So you start off with mu. You evaluate a and b using rational interpolation, and then you find out. At least you know that the pi's are determined at least as the irreducible factors of b, and then once you have the p's, once you have the pi's, the di's are also determined as the coefficient of the partial fraction expansion of a over b. Yeah.
Is beta assumed to be integer?
No, it's assumed to be rational.
Rational.
That's all. Yeah. So that's the only assumption that comes. Okay. It's not an assumption really, because even in any kind of sort of exact computation result, you at least need to assume that beta is either rational or algebraic with some small degree and so on, and all of this would work in that setting, I think. So that should be. Yeah. Okay, so that's a sketch which should sort of convince you that this can all be made to work, and in fact, it turns out you don't need to really do factoring. You can do something much simpler to sort of combine these two steps in one and find P and D once you have A and B. And so basically the conclusion is that you can sort of do the symbolic integration as long as you can do this polynomially many n evaluations of mu at some different values of lambda. And this can be done in ways that are very similar to what has been done earlier for partition functions. So again, you modify the graph slightly to sort of simulate these different lambdas, but now you need to be a little bit more careful because you're trying to compute these averages rather than a partition function, and things can get a little bit tricky. So there's some cases in which we don't know how to do the simulation. So one of these is the anti-ferrometric Ising model with field. But in general it works, and then basically once you have that, you can just plug. Once you have this strategy for simulating different values of lambda, you can just plug it into this, and complete the deduction. And this is completely sort of model agnostic. The only thing it used is that the average that you're looking at is some derivative of the free energy, and that's sort of true for any interesting average. That's how the free energy is defined in some sense. So basically the only model specific detail is the simulation of different lambdas or different betas in the model. Okay, so that's the end of the talk. So basically, just as a summary, so we saw two ways of attacking this problem of the complexity of computing averages. The first one was precluding common factors. It somehow is not general enough to work for all the problems that you would want it to work for, but it leads to new results about zeros of partition functions, which are potentially of independent interest. And the second one was symbolic integration, which is somehow more general, but somehow doesn't tell us anything new about these specific models. And so at that note,
So you had on one of the slides, you had Szegedi. Which Szegedi was it?
Mario Szegedi.
Mario.
Yeah, I should remember first name.